We all know and love rockets. They're big, they're cool, and most importantly, they're fast. Or are they? Sure, relative to how fast humans can travel on Earth, rockets are pretty fast. And rockets are fast enough for traveling short distances in space, like to the moon, where the journey is only 3 days long. But the moon is just the moon. Take Alpha Centauri, the closest solar system to our sun. It takes 6,300 years to get there by rocket, which, of course, is a problem if humans are ever going to become a spacefaring civilization. So we need faster rockets, and I think that antimatter propulsion could be the answer, allowing rockets to travel to 7 times the speed of light, reducing the Alpha Centauri trip to just 7 years. So first off, what is antimatter anyway? Well, antimatter is kind of similar to matter. Their fundamental particles have the same mass compared to their matter counterpart, but have opposite charges. A normal atom usually has one or more negatively charged electrons orbiting a nucleus made of neutrally charged neutrons and positively charged protons. In an antimatter atom, positively charged positrons orbit a nucleus made of neutrally charged antineutrons and negatively charged antiprotons. That's great and all, but how does that get us from here to here? As you may have learned in physics class, the kinetic energy is equal to 1/2 the mass times the velocity squared. I'm going to move the mass to the other side of the equation, so now, in rocket terms, it's kinetic energy provided by the propellant divided by the mass of the propellant, which is also known as the specific energy, and that's equal to 1/2 the exhaust velocity squared. So according to this equation, the higher the kinetic energy provided by the propellant and the lower the mass, basically meaning the higher the specific energy of the propellant, the faster we can go. And let me tell you, antimatter can create a lot of energy for not a lot of mass. The fundamental principle behind antimatter propulsion is annihilation. Annihilation is kind of like jousting. So let me introduce you to the players. On the right, we have a little feisty positron, and the left is an equally menacing electron. Wait a second. What's this? Warning, it explodes on impact. It's probably fine. Anyways, before I was interrupted. Wait, what? Oh, I forgot. When antimatter and its matter counterpart collide, they both explode, literally annihilating the two particles and converting their mass into a very large amount of energy. The amount of energy released can be calculated using Einstein's famous E equals mc squared equation, and you can imagine that's a lot of energy. In an antimatter engine that uses annihilation, antimatter would be stored in what's called a penning trap, which uses magnetic and electric fields to prevent antimatter from colliding with nearby matter. And then it's released for annihilation, usually with a positron into an electron. Because converting mass directly into energy is so efficient, antimatter has a very high specific energy of around 90 billion megajoules per kilogram. Remember, specific energy is the kinetic energy divided by the mass. Compare that to a common rocket fuel like RP1, which only has a specific energy of 40 to 50 megajoules per kilogram. You would need to combust around 1.8 billion kilograms of RP1 just to attain the same amount of energy as just half a kilogram of antimatter and half a kilogram of matter. Now that's a lot of RP1. I'm sorry, does that mean dead? Well, that's it, and that's why some people would consider antimatter the king of rocket fuels.